happy to have Arnab from Monash University. Arnab works on a variety of topics in collider physics, particle physics. He is PhD from TIFR. He is his first postdoc from Monash. Now he's moving to the University of Barcelona. They will be talking to us about Dark-SMEFT Higgs and HLs.
Thank you, Ranjan. Thanks. Hi, everyone. Thanks for having me here and giving me the opportunity to present my studies. As the title suggests, we'll use two LHC probes, monojet and semi-visible Higgs decays, to study the Dark-SMEFT operators. I think all of you know about SMEFT, but let's have a brief recap, and that will actually help me to start my talk. So the idea of SMEFT is that, let's say we have a collider operating at E2, and we are plotting the invariant mass of some resonances. Then we expect to see this resonance peak at this collider operating at E2. But if we are at E1, then we should miss this peak, but we should get some effect towards the tail of the distribution, which we can take into account using the effective field theory. For example, if we are at LHC, then we saw the Higgs peak. But if this is a resonance at 3 TeV, then we will not see this, and we'll get some EFT effects for that resonance. Now, in that case, what we do is we integrate out that heavy mediator, and we are left with some higher dimensional operators, which we add to the standard model Lagrangian, and we call it SMEFT. Now, generally people argue that since we didn't discover anything at the LHC, discover any BSM at the LHC, probably all the BSMs are residing above the TeV scale, okay? Which could be correct, and in that case, SMEFT is the correct theory below the 1 TeV scale, let's say. But this may not be a complete picture. Let's say we have some light BSMs which are not completely ruled out. For example, we studied the single dark matter in the next to minimal supersymmetric standard model, and this paper from 2024 is I think the latest paper on this topic from IISc actually, and that tells that we can even have of the order of 1 GeV dark matter, which is still allowed within all the constraints that we have till now. We can also have dark matter around 100 GeV and allowed by all the constraints that we have. So it may not be fully correct that all the BSMs are residing at scale above 1 TeV, and in that case, what we should do is we should extend the SMEFT with some extra light degrees of freedom, and I'll come into that. Before that, I just wanted to flash out this diagram. This is not directly relevant to this, the point I want to make in this slide, but in this case, this is actually a diagram from this paper we did in 2020, where Higgs, standard model Higgs, is decaying to neutral dark matter of the order of 1 GeV and some standard model fermions. So you see, this is a semi-visible Higgs decay, okay? And this is an example of semi-visible Higgs decay in the UV. Later on, I'll come where we can use a generic semi-visible Higgs decay study in the context of EFT, okay? Now coming back to my topic, it may be better to add some light degrees of freedom with standard model before we write the SMEFT. So in that case, so let's say this is my SMEFT where all the degrees of freedom are standard model degrees of freedom below some UV scale lambda. But in this case, we would extend the degree of freedom by one extra dark degree of freedom along with the SM degree of freedoms. And this model we'll call Dark-SMEFT. So dark matter EFT is going on for a long time, but these are the two papers where they tried to, and actually did, they wrote down the complete basis of this type of scenario where there is a minimal extra light degree of freedom along with the standard model degree of freedom. If you want to work on this, I would suggest to look at this Monash paper at 2022, which actually takes into account some extra gauge invariance and stuff for the vector type of dark matter, and that is, I would say, more correct in different senses. So this is what we call Dark-SMEFT. Yeah.
So the dark matter here is not part of EFT?
Yes, it's part of EFT. So
then you write down the Lagrangian dark matter separately. So why is that?
yeah, so there is SM Lagrangian, there is some kinetic Lagrangian of the dark matter.
Okay.
And then all the EFT operators, including the standard model and the dark matter.
When you say dark matter EFT, that means the EFT which respects the dark matter symmetry.
Yes, it does. So it's a standard model symmetry plus some extra what you can add. Yes.
Like, what's the difference between like just dark matter EFT?
It can be actually other dark matter EFT, but in this case we are talking about the electroweak scale. For example, you can write let's say Q bar Q, chi bar chi kind of thing, but at the electroweak scale this is 6. So let's say I have, we can actually write chi by chi bar chi, but to give, I think, the dark matter mass and stuff, you actually need a Higgs to write down this thing. Actually, I forgot. But in this case, you are actually removing all the heavy degrees of freedom, Higgs, W, and stuff. But for this Dark-SMEFT, you take all these Higgs, Z, W, all degrees of freedom, and write the dark matter EFT. Maybe one point, if you consider, for example, the Rajaraman's paper in 2010 working on dark EFTs, then it is only standard model quarks and leptons with dark matter without any like heavy fields. But in this case, they add the electroweak scale sector standard model and add the dark. So you can actually relate this to the previous dark EFTs. You can have it in that. You can have TT bar, you can have gauge bosons, everything. So this is kind of a high scale dark matter EFT. Yeah.
So there we consider all such possibilities. That's why
Yeah, so it is true that these possibilities are like there from, it's going on for a long time. In different papers they are there, but they made a complete basis out of it.
some basis
All possible operators that can be in the electric scale.
Some couplings may be correlated or something.
Yes, those couplings are correlated with whatever you write at the low scale. So you can take this as a wave, and then it will be a low scale EFT.
All the couplings are not
Yeah. No, they are correlated. Yes. Okay. So within this context, we'll study two things. One is monojet, where we'll obtain constraints on these EFT operators from the LHC data from monojet searches. And in this case, we'll mainly focus on a key question that when we are interpreting LHC data in the EFT framework, which range of the energy are actually compatible with some UV that we have, or which is the reliable range of EFT interpretations that we can have. Okay.
So are What's the difference between ADFT and the dark matter? Means ADFT has some light AFT has some basing, but that not necessarily dark matter.
LEFT is when you integrate out Higgs top gate bosons. So that is only you are left with.
That also has some basing.
Yeah, you can also extend LEFT with the dark matter. It will be a dark LEFT without the Higgs top and all this thing. But in dark SMEFT, you have this heavy standard model particles. Yeah. And another thing, we'll try to see how much of the parameter space we can explore with a new probe called semi-visible Higgs decay. It's not completely new, but I'll come to it. So going forward, let's start with monojet. This work I did with Michael in New South Wales University and Herman in Monash University. And we'll start with the set of dark SMEFT operators that affect the monojet searches. So in this monojet case, we focus only on scalar dark matter. And there is a list of scalar dark matter that is possible, but we choose a subset only which is related to the monojet search. Okay, and this we just call phi SMEFT. Now, in this context, the context of monojet searches, the validity of EFT is studied from long time. If you talk about like which is a reliable range where we can believe our EFT interpretation, we can think of it two ways. Let's say we have a cutoff scale lambda, then the scattering energies, the center of mass energies, should be below the scale lambda. Otherwise, you are, yeah.
So does it matter whether the phi is complex or real?
In this case, no, you can take phi complex, so it will be phi dagger phi. Yeah, and the only in some calculation there will be a factor of 2 difference because of counting the degrees of freedom. Yeah, otherwise it will be same.
What is QLE? What is the P?
Oh, P is the generation index. So we can take quarks of first 2 generation. I am taking quarks for first 2 generation. So it can be 1, 1, 1, 2, 2, 1, 2, 2. So basically up charm, up like that. US or DS, those things. Okay. So talking about the validity of EFT, people used to say that this is actually correct. I would actually prefer this one. So this is a proxy of the center of mass energy where the scattering is happening for the monojet, so phi, phi, and jet. And you require that this scattering energy is less than my EFT cutoff scale lambda. Now this is a very strict constraint. This cannot be, maybe not that strict in a strongly coupled scenario. We can have the valid EFT somewhat arranged below lambda, and in a weakly coupled scenario, lambda is a good limit. But the problem with this type of measures is that when you try to interpret the experimental data and try to put constraints on the EFT, then you cannot actually construct this observable in the experiment because these phi's are coming as missingity together. You cannot construct the form momentum of each phi. So in that case, these observations, this requirement on the EFT is not possible when you are interpreting experimental data. So what we do in this case is to rely only on the what we can reconstruct at the collider. We do this study using missingity. Okay, and in this case, we do another thing is, let's say you have our EFT cutoff at lambda, then we expect that below lambda, the EFT description should match an UV that is residing above lambda. Okay, so if we draw bounds from these two frameworks, we should get some similarity. So that we do step by step in this study. So we have our EFT, we choose one UV model that can be a UV completion of this Dark-SMEFT, and then we do a step-by-step check in which missingity range my EFT is actually compatible with the UV. That is one kind of acid test that we have, that my EFT framework is working or the EFT interpretations are reliable. Okay, so this is the UV model that we take, which is a simple extension of the standard model with two vector-like quarks having the same quantum numbers as the quark doublet and the singlet, and one extra singlet scalar phi. Okay, all are odd under Z2, so you have to have two BSM at each vertex. Okay, so this model we called VLQS, and this was actually proposed by Michael, Herman, and Raymond, and all these people to actually explain one B2K nu anomaly that was there in the Bell experiment. Okay, so now these are the monojet diagrams that we can have from the UV and the EFT. So the first two are T-channel exchange of the vector-like quarks, and the last where we can have a on-shell Q and D vector-like quark, and the EFT counterparts are kind of easy. You squeeze these sectors and you make a blob, which is the EFT, and these are the Dark-SMEFT interactions that we can have. So these are a subset of all the Feynman diagrams that we have, but generally these are the classes of diagram that we had in these processes. Now, we do one thing. Let's fix the mass of the vector-like quark at 3 TeV and plot these observables for the EFT and the UV. Okay? So the left is the invariant mass of the two phi's and j at parton level, because at the detector you cannot get it. And the right plot is the missingity of this system. So you can easily see that for this fixed parameters, we get EFT and UV compatibility up to some range, and then the EFT deviates from the UV. Okay, EFT deviates from the UV. For the missingity variable, which we are interested in, we see that up to around 350 to 400, EFT matches with the UV very well, and after that it starts deviating. Okay. Now, this is for one mass point. So if we increase this mass to very high mass, let's say 6-7 TeV, then that producing that mass is not possible by the LHC. So
your cutoff scale is 3 TeV.
Yes.
But your 5 SMFT is going above 3.
Oh, this is I think just a bin effect. It's going over that bin. Huh? Yeah, it's something like that. Yeah, it's a binning effect.
Yeah, but then I would try to be less than that.
Yeah, actually, yeah. So in this case, to tell the truth, we didn't put this condition that it has to be lambda, less than lambda. We just plot the distributions. Yeah, if we extend it, it may go a bit above, and this part. Okay. Yeah, for the UV complete, we have a bump coming above 3 TeV or so, and that is basically due to this third diagram where the Q and D can go on shell. And that is the actual problematic diagram where we can lose the reliability of the EFT if we compare with this UV model, which I will come later.
So this plot should depend on the width of this part.
Yes.
So depending on the width, if it is narrow width, then probably EFT will be valid.
Yes. Yeah. Yeah.
How do you fix that?
So we actually take the width into calculation. So depending on the parameters, my width change and my predictions are also changing.
No, but if you know the theory, then you can just do the full calculation. You
Yeah.
don't need EFT, right?
Yes.
So like the situation where you don't know, the width, how do you take care of this kind of?
So for the EFT you are talking about?
Yeah.
What should EFT there is no width.
No, no, I'm saying that, so you're saying that there is a real physics, like
Uh-huh.
particle, that, so you're trying to parameterize the tail of the distribution. And
Yes.
The tail depends on the width of this particle.
Yes.
Outside the center of mass energy or something, but the shape will depend on the tail of, like the width of the distribution.
Yes, it will
How do you
depend.
parameterize that?
In
Or
EF,
you just assume narrow width or something, or you just write out the effective operator.
no, in the
I'm saying that just go to that plot. So here it shows that up to 2 TeV,
Hmm.
it doesn't matter, right? But if you change the width of this particle,
Hmm.
probably it will matter, probably starting from say 1.8.
it will.
Yes.
It will.
That we don't know.
That we don't know, but that is fixed by the model parameters. So when we match the EFT with UV, then I can, so let's say I have some values of this UV parameters where I can have some width, and we can match with the UV to say that this region is not working and this works. So if you make a wide width, maybe in some region it will come to this part.
And you don't know the model.
No, I don't know.
So then you don't know the width also.
Yeah, I don't know.
So then how do you actually know where is the validity of your
Okay, yeah. So this, so in this case, this is just an example. So this validity, like whatever I say that this region is not valid, this is only applicable to this UV. If you go to another UV, this may not be the case.
Yeah, there is a resonance.
Yeah, so in the previous slide you showed the resonance and the tail part falls in the.
There is not an S channel. Here this is producing the Q and D. That's not the S channel.
This is not an X channel, but there will be some on-shell width effect.
Yeah, but that's why maybe it's not so.
So that I understand. But there should be some effect of the width. Right?
Hmm.
That's what I
Yes. So if I put it this way, that whatever EFT validity results I draw from this observation is only valid for this model. If we go to another model with different widths and stuff, then this is not perfectly like extendable to that sector. So you have to do another calculation. But in this case, what we can have is get a rough estimate of where we should expect the EFT validity in case we want to interpret the LHC data with EFT.
For that, I need to see also the stand model thing.
Huh?
For that, how they estimate.
Yeah, standard model backgrounds are there, but they are
Yeah, but then, so then I can say, right, where is the SMEFT, this 5 SMEFT being above the standard background? And I don't see it.
Oh, but
match the full theory with EFT, and he's saying that up to some scale, say less than 2 TeV, it's really matching with the full theory.
Hmm.
So if you use EFT below 2 TeV in this plot, so you are safe.
Yeah.
That's what you are saying.
okay.
In the left plot,
Hmm.
so if you apply the criterion that invariant mass of this pi phi j has to be less than 3 TeV, then also you have a small bar that just
Here? Yeah, that's probably a statistical thing, but I'm not sure about it. It's generally it is true that putting m phi phi j less than lambda works, but I'm not sure in this case. Maybe I need more events here. But as I said, this uses the parton level information, so I do not want this to be used when I interpret LHC data in our framework. So I will use that.
Also, so the energy to reach this SMEFT, 5 SMEFT matches real QS, those two plots are different.
Yeah, because
It matches to the say 500 G.
yeah, because so this is not a proxy of the center of mass energy. So some part is missing. So you do not reconstruct the full energy here. So this has to be different actually.
So from this missing energy or from this parton level mass distribution,
Hmm.
how can you say that the lambda is at 3 TeV?
We actually cannot. We are doing the other way around. Let's put lambda at 3 TeV and check where it is matching or not. Oh, right. So if you are saying if I see some deviation, should I How would I know it's 3 TeV? In this case, you cannot. So then, if you expect something around this, maybe you need to do other search where you can reconstruct the resonance. Here you cannot, because these are missing.
Exactly.
Huh.
So, and reconstructing the resonance,
Yeah, needs some.
resonance means we should know the width.
What like you would try to do it for effective field, there will also get a limit on say casting by lambda, right? So you just push the lambda above some number and then you want to say, right? So like you will always get a limit of some g by lambda.
I think she's asking that if I get some deviation in the MET spectrum, how would I know what is the mass of the UV?
I mean, how will it interpret?
So,
If you like stick to EFT, probably you have to assume that lambda is still above some number and then you can use the EFT and then you can get
Like,
the
we have to rely on model and people interpreting.
yes, because like you cannot get a like independent limit on lambda. It's always g by lambda.
Yes.
You assume that lambda is high and then you choose your g. Because if you are stick to like EFT model and if it really looks like a bump or something, then you just don't use EFT.
Yeah, so that will be kind of direct search, but I was asking about this kind of like this
In
image.
that case, you should always push lambda
Yes.
above some number.
you'll get some idea.
Yes.
Then you will do direct searches to measure it.
It's always
So this will imply, I mean, this will, from this we have to do a direct search. to
Yes.
interpret something.
Yeah.
Yes.
Okay. Now I expect that if I push my lambda far above, EFT and UV should match, one thing. And second, if I restrict my MET around this region, then also the EFT and UV predictions should match. And that we see in this case. So let's say I take all the Atlas bins, which starts from MET or PT of jet greater than 200 GeV, and all the PT of jet above it is included in those bins. So in that case, if I increase lambda, I get EFT and UV predictions of the cross section to be similar at around 4.5 TeV or something like that. If we restrict ourselves in the bins below 300 GeV from like for the monojet, and we plot the cross sections for different scales, we see that around 2 TeV we get matching, which is expected from this like figure. Like if you are restricted here, the predictions of the cross section should be similar. So that's just a check, and here we also get some idea of the where EFT and UV should match if I am taking all the bins. But yes. Yes. So let's say it is like that. So let's say we are putting a PT jet greater than 200 GeV and count all the events. And in the second case, we are restricting 200 to 350, so only this part, and count the events there. So in that case, the total count of EFT and UV should match, and that is what is happening here. Okay, so these are just some sanity checks, but now what we do is use the Atlas data after full run to constrain the parameters of the theory. Yes, public means in their paper they have the number of events with uncertainty for different MET bins. You can use that. Yeah. So the Atlas data is published this way. So they have MET bins starting from 200 GeV and up to 1200 GeV. So it can go above to 1200 GeV. So the bins are like in two cases. One is inclusive, where you have, let's say, MET greater than 200, greater than 250, like that, and exclusive, where you have, let's say, 200 to 250, and 250 to 300, like that. So in this case, you can easily see that if we use this inclusive bins, we are always taking the high PT events into account. So this is not a good thing to do in our case, because we want to check the EFT-UV value matching. But so we use this thing where we can see that we can cut off our LHC observation up to some energy. So we use the exclusive bins here. Yes.
What if the PT of the jet lesser than 1 meter? Does the lambda pushes or
Can you tell me?
PT of the jet
Huh?
lesser than 1 HG?
Yes.
Greater than 100 G.
Yes.
The lambda shift to 4 to 5 T.
Lambda. No.
So that
Yeah.
here
Yeah.
the PT of the jet is greater than 200 G.
Oh, so you're saying if I
It's 4 T.
if I use say PT of jet greater than 100 GeV, then it should match a bit earlier, I guess. I think it will be earlier because you are adding more low energy events, and in the low energy event there is not much problem. Problem is in the high energy events. Is it clear? We can discuss. So I will not go into this calculation framework that I use, but what I basically do is I have some parameters in the UV or EFT, let's say, and I recast the atlas analysis. Using that recast, I can generate events in my some simulation chain, and I can produce events that exactly mimics the atlas data. And from that, I can get the number of events as a function of the model parameters. Okay, so we do some calculations. I have made some framework here with which you can get these numbers for each bin, and then we can do a polynomial fit to get this function for each bin. Now we have this function, which is a function of these parameters, and we have the experimental data, let's say some delta n, and we know the uncertainties. So we can actually make a chi-square and minimize the chi-square to fit these parameters, and from the chi-square minima we can actually plot the 97% confidence level allowed regions of these parameters.
So what's the definition of monojet in this analysis?
Definition is this. So different bins with different PT cuts.
What's the jet? Or how many jets they allow?
One jet.
Exclusive or inclusive?
Exclusive one jets.
Exclusive or
Yes. So to be very specific, exclusive one jet above 200 and 2-3 other jets which are very low PT. Okay.
then it's inclusive.
That is inclusive. Yeah.
Monojet doesn't mean that there is only one jet. There may be more jets also. But the highest PT should be
Greater than 200, and above 200 there should be only one jet. Only one jet. Okay. So using that framework, I calculate the allowed regions. Which is what we can obtain from this atlas data.
In your file, SMEFT or in the full UV model?
I do it for both. Yes. And
Equally compare the time.
yes. And that's the thing. So I do it for both. So these are the UV model parameters. I get this kind of allowed region. For EFT, I get this kind of allowed region. And this blue thing is what we can, is a projected region at the HL-LHC. So this is the allowed by the current data, and this some projections. The whole, yeah. That's actually very important in our case. So I'll tell about it. So the thing is, if I go back to this plot, you see here in the bottom panel, I plot the pool for the atlas data in different met bins. So these are the different met bins they have. And you see for a bin around 1000 GeV, the data deviates from the standard model by almost 6 sigma. Okay? So if I go to the UV, then around this region, I have a lot of events to explain this deviation very easily. But so just a little bit of deviation in the parameter, this comes into the the UV description. But for EFT, you have to have big parameters to get this deviation into account. So
you were saying that the green thing is the data.
green thing is data.
It is the data. Right?
Yeah.
And the upper panel you have UV versus the EFT comparison.
Yes.
And you're saying that as we are much higher in the PT, the UV can easily give the events and
Yes.
really not the EFT.
Yes.
This you're saying. But the UV also hasn't taken up to let's say 2000 GeV PT. That doesn't reflect in the data.
Oh, this one? This is?
The UV.
Oh, UV?
Yeah.
No.
It is almost approximately flat up till 2000 GeV.
Yes.
But that doesn't reflect in the data.
No. So this is my Monte Carlo prediction, which does not have to be compatible with the data. Data is what we have, like the deviations from the standard model that we have seen in the data. So these are not actually in the numbers, but how many sigmas they are away from the standard model, which is independent of what we predict in the Monte Carlo. So you are saying that since there are events, we should also see some deviations in this?
Increase the model.
Yes, yes. So in this case, I would say that this is some anomalous thing in the atlas.
You don't have the, like, I see the model, there is no data. This is data or there is no?
This is the atlas data.
Okay, so it's not from the
No,
variable picture.
no. This is separate. Just we wanted to actually understand his points, why there is a hole there. And that's why we plotted the atlas data like this.
So these are two different things.
Yeah, two different things. Just to compare the data with my model prediction. That's it. Okay, and I'll show in the next slide. Yeah.
It's deviating like 6 sigma, 5 sigma deviation.
Yeah, like 5 sigma deviation.
How many like excess events are there?
That actually I forgot. I have it in the backup slides. Let me. Oh,
But that
looks.
is only local signature.
So for the EM10,
The last, probably it's the last week.
yeah, this is the EM10 bin. This bin. So if you add like, so yeah, you add 60 to it, and then you'll get something like that.
But after that, there are
Yeah.
more beans actually.
Yeah, there are more bins. So that is something anomalous going on in that bin. I don't know what is going on. But that's the effect.
But in inclusive, there is no such problem.
Inclusive, looks like there is no such problem. Yeah, looks like it's within 2 sigma or something.
No, but the question is, if your like data is like deviating 5 sigma from at least one bean, then your like quantic uncertainties and all these things are correct or not? Like I'm asking atlas.
Yeah, I'm not sure about that. But maybe they have seen it and
One bean.
yeah, this is one bin. And I'll show you what happens if I remove the bin.
So the inclusive.
So what is the, sorry,
you know,
no, no, no.
Yes.
So the inclusive versus exclusive. So the exclusive one has an uncertainty of 10 and
Okay.
the inclusive one 60.
Yes.
So is it like the exclusive one is more precise because given that it has uncertainty 10, you see 5 sigma,
Actually,
you
yes.
see 60.
Actually, yes.
So maybe somewhere you lost
Yeah.
answer.
Actually, yes.
And then because
Yeah.
it's not clean.
Yeah, actually, yes. You are right. So yeah, if I use the inclusive data, I actually checked, I get a weaker bound because of those larger uncertainties. So maybe yeah, that's the reason but I'm not sure why that EM10 bin is like abnormal in this case. But you see here, so we'll come to this slide.
What is the global significance of that?
Huh?
What is the global significance of the EM10?
No, I think it's not. I don't know actually, but I think it's, if you take the global thing, it's within standard model, like 2 sigma or something. I have to check the paper.
For the first events, observational events are quite high.
Which one?
So if you take the global,
Huh?
I assume that you have
Yeah.
taken all of the data.
Yeah.
The first few weeks
It's too high. It's too high.
I don't think it is.
Yeah.
Globally, it will not.
Globally, it didn't make any. Otherwise, there will be a. But yeah, it's not globally much significant. But you see, I'll come to the plots later. But let's say this is the some allowed region with the EM10 bin. If I remove the EM10 bin, there is no blob. So that blob was due to the EM10 bin. Now I'll come to this plot. So what I do is, I use these matching equations to transfer my bounds on the.
Make this because you're saying that anything that is white, that is allowed. What does
Yes. No, anything is white is excluded. So standard model is excluded for the EM10 bin. Yeah. So using these matching equations, we computed this using monojet. I forgot to write it here. But we transferred the bounds from the EFT plane to the UV plane. Okay. So basically this blob will go to some UV plane, and then we plot this together. So the blue region is the bounds on the UV that we translate from the EFT bounds, and the whatever this is, red is the what we directly get in the UV. So you see the UV bounds, let's consider this one now. UV bounds are much stronger than the EFT when we take all the bins. But if we restrict it to bins up to 350, EFT and UV matches very well. Okay, so that's the thing. So with that, I'd say a few things, that we do not know the UV model. So maybe this 350 is not 350 for other model. It can be 500, it can be 600. Or if I extend my UV scale from 3 TeV to say 6 TeV, then I think I can extend the MET region up to 800, 900. But this is just an example that if I have my UV at 3 TeV and I use the MET proxy, it will be, so in this case, it is around 10 to 15% of the UV mass where my EFT is reliable. Okay, so basically if you come down in the UV scale, so these are actually the first 2-3 Atlas bins. Okay, so only these first 2-3 Atlas bins are reliable if this were my UV model, and all these other bins are not reliable. So the thing is, whenever so we cannot go take all the UV models. So what we can do is we can report bounds up to different values of the MET max. So I do bounds up to 350. I'll put another bounds up to 500, another bounds up to 600, and then depending on my scenario, I'll choose which EFT bound is good for me. So, yeah.
So there is, as far as I understand, there is no problem with the EFT, but the problem is if you translate to your actual model, right? So otherwise, like if you just assume EFT, other bins are also fine.
Yeah.
But if you like translate your EFT interpretation to some UV complete model, then the problem arises.
Yes, so I'll put it this way. So let's say I do not know the UV, and UV scale could be at 10 TeV. Then there is no problem with EFT at any MET pin. Okay, but once you somehow say that this should be my UV, and that is actually above the scale we are truncating the UV 1 TeV. So we are at 3 TeV. So generally we expect that maybe up to 800, 900 it should work, because it is 3 compared to 1. But actually it is not. It is working up to 350 or 400 GeV. So that is quite a big jump from 1 TeV to like 350, 400. So that largeness is what we are seeing here.
But if the data is
Hmm.
then there is no problem, right?
If the data, no, actually there is, because let's say if the data is consistent with standard model, but you are plotting some EFT bounds here with all the data, and you know your UV theory. In that case, maybe this using all the data which are compatible with the standard model are also not very good. I would say the problem is in the EFT once you fix the UV. Yeah. But UV is complete. You know if you know the UV theory, there is no problem with that. You do not have to truncate it at some scale or something. Yeah. Oh, yeah. In that case, I scale these things with luminosity, and I assume that there is no excess in the events.
But for HL-LHC,
Hmm.
that trigger will be different.
Which thing?
Like say, suppose here you have applied say JPT greater than 200 G.
Yes.
Now it's now the correct. This is probably for RAM 3.
Yes.
But probably for HL-LHC it will also change.
And
Simple translation cannot work.
simple translation may not work. Yes.
It will be 300, 400.
Yes, but like from like energy scale wise, it will go from 13.6 to 14, so not much.
Phyla, they have to increase the threshold.
That's true. That's true. That's true. Yeah, that's true.
There may be a change in the threshold.
Yeah, that's true.
Maybe I will probably change it.
Yeah. We also change the uncertainty. We also change the uncertainty 3000 by 140 times sigma 0, let's say, or sigma LHC. So this is a kind of optimistic scenario where we improve the systematics. Okay. I don't know where I am. You can tell me when to stop. I'll just take 10 minutes to tell the other thing. Okay, so this is the thing. Now I'll quickly go.
I have a question. So here you talk about the monojet searches, right?
Yes.
So can we also do this for let's say the missing PT plus some engagements?
You have to do it again differently and see where things stand. Yeah. I mean, you cannot directly.
Just optimize for like monojet searches, or you can also do that?
So yeah, my study will be only for monojet searches that Atlas did. I think if you go to the searches for another search for CMS, there was another paper which was a bit less sensitive than Atlas. This might also a bit, like it can change a little bit. But the overall message is like that. You have to be careful. Now I'll quickly go through the rest of it, of this part. Like we take other experiments and other bounds to see the like the constraints on the EFT and UV parameters. So here we calculate one theoretical constant, which is a perturbative unitarity for this EFT operators, and for UV I just take perturbativity. So that is the thing, and also we compute the dark matter direct detection constants for these models, and actually we calculate it for the EFT, and since the dark matter experiments are at 1 GeV scale, so we can just use the matching equations to get the bounds for UV. There is no problem of validity. Yeah, and also we calculate the thermal relic density using MATDM. Now putting everything together, it looks like this. For the EFT parameters in a thermal dark matter scenario, looks like everything is ruled out. There is no place for dark matter. The monojet searches are actually much weaker than the direct detection. Okay. For the gluon operator, the monojet searches are strong because of strong gluon PDF. So we can get some regions where monojet searches can be better, this high mass region and this low mass region. Okay, so these are individual operators, but if we do operator combinations, we combine two, three operators together in some way, then we can get some cancellation in the dark matter direct detection experiments, and there the monojet searches can do better. Yeah. So I have this equation, and let's say this is C11, this is C22. Okay, two different operators. So C, the quark operator with DD, and this is quark operator with SS. Then we can compute. So there will be one value where CDD is minus something CSS, where you can get a cancellation between these two parts. So that cancellation I'm using. There is one caveat here, that these Panda and LZ experiments are xenon experiments. So the Z by A ratio is different from dark side and deep, which are argon experiments. So the cancellation point is not the same for Panda LZ versus dark side deep. So you cannot wipe out everything. So you have to minimize both of them to get some region where both of them partially cancel. Okay. So this is the thing, and similar things for UV. You can, like if you make a combination of the UV parameters, you get some region where monojet can be important. Okay, that's it for monojet. I'll quickly go through the other thing, which is semi-visible Higgs. So we try to produce the semi-visible Higgs through the ZH channel, because ZH is very clean. And we do two analyses. One is where Higgs is decaying to 2 leptons and missing ET, while Z is going to 2 jets, and another where Z is going to 2 leptons and Higgs is going to 2 jets. So the final state is same. It is 2 lepton, 2 jets and missing ET, but the topologies are different. One is hadronic Higgs decay, one is leptonic Higgs decay. Okay, so this part of the Higgs decay is visible and this part is invisible, so we call it semi-visible. Now, the point is that this is the second study we are doing for this semi-visible, not actually second study in a generic framework, because the diagram I showed you much before is also a semi-visible Higgs decay, but in the UV. Here we do a generic study for semi-visible Higgs decay, and this is the first study by Aguilar Saavedra and some team, where they do the semi-visible Higgs decay where Higgs is going to BSM plus a genuine Z. Okay, in that case, this background Higgs going to ZZ star to 2 neutrino and 2 fermion they showed that this is a irreducible background, and in analogy with the neutrino floor in dark matter experiments, they call it Higgs neutrino floor. So you cannot get rid of this.
Maybe reducible if the dark matter is very light. If the dark matter is heavy, then it need not be reducible. Then the kinematics of the effect will change.
If the dark matter is heavy, if the dark matter is
and allowed to decay around it.
I don't think so, because this problem is that you can reconstruct Z from these fermions, and then
if you have say 20 GeV dark matter,
yes,
then should the energies carried by FF bar change?
that will actually go to the total thing will go to the missing ET. Yeah, so even if the mass is higher, missing ET is basically the PT of the Z. So PT of Z should not be different, right? Maybe I'm wrong, but I'll check that. But yeah, probably it is not, and this showed that this is an irreducible background. So what we do here is we first observe that this is not a complete picture of the BSM. This is a very small subset of the total BSM possibilities that we can have, and we should do a generic study to really say whether this is reducible or irreducible. This is important because in one Atlas study, they commented that since this is irreducible background or some similar reasons, we are not exploring this semi-visible Higgs channel. But maybe it is reducible for different other UV scenarios. So what we do a generic study of this semi-visible Higgs using these Dark-SMEFT operators. So these are the set of operators that can lead to the semi-visible Higgs decay, where actually I forgot to write one operator. So there will be another operator which I call DH chi 2, which has a gamma 5 here. So gamma mu gamma 5 current is there. So 4 and 6. So there are 6 operators. This goes to leptonic Higgs decay. This goes to hadronic Higgs decay. Now, one more thing is that if you see this derivative type operator, there is Z hiding in this covariant derivative. So you can have Z to phi phi bar or Z to chi chi bar decay, which is invisible Z decay. So we should get some limits from invisible Z decay. Interestingly, it looks like there can be a Higgs to phi phi vertex, but there will be none. Because this derivative operates on two sides, I can show that the Higgs phi phi vertex actually is not there. It gets cancelled. So either you have Z phi phi, ZH phi phi, or ZHH phi phi. I'll come to the other thing, but let's move on. So these are the diagrams that we can have. This first one is the standard model diagram, Higgs going to ZZ star to 2 neutrino and 2 fermions that they called irreducible. These are the 3 EFT possibilities, where this last one comes from this Yukawa type interaction, and these two comes actually from the derivative operators. Now you see, if this Z attached with the fermions are on shell, then we can actually exactly have this diagram where you can reconstruct the FF bar mass and you cannot distinguish between the standard model and these diagrams. Okay, so this is the case where we could have the irreducible standard model background that is proposed by the Saavedra's paper. I said could have because actually what we saw here is when this operator is present, both these diagrams should be there, and when Z is on shell, there is a cancellation between these two diagrams. So the on shell part of this diagram where Z going to FF bar is actually there in very small amount. So in all the cases, almost all the cases, Z attached to the phi phi is on shell and this is off shell. Okay, and that's what we see in these diagrams, in these plots. So if I plot the dilepton invariant mass, in the irreducible case, I would expect a similar Z peak like in standard model, but in this case, because of the cancellation, the leptons are coming from off shell Z, and we get something here below. And to cross check, if I plot the parton level invariant mass of the 2 neutrinos or the 2 phi, if you see the 2 phi for this red, purple and black, they are actually picking at Z pole. So the on shell part goes to the invisible phi phi thing. So actually what they thought that this Higgs to ZZ star to 2 neutrino to fermion would be an irreducible background is actually not true. You can reduce it with the invariant mass, lepton invariant mass cut for a generic scenario. Okay, there could be some scenarios where there is exactly only one diagram with Z and not the other diagram. There it would be the Higgs neutrino floor, but otherwise I can reduce it. Okay, so moving, any question? Yeah. Either electron or muon. We took both.
So you have electron, dark matter, Higgs coupling.
Yes. Yes.
So in that case, E plus E minus 2 dark matter, Higgs at play.
Yes.
Possible, right?
Is possible.
So is there any bound?
I didn't see any bound, and probably we should calculate it. There should be one, yeah. We actually talked about this, so this could be another channel in future collider, or actually in LEP. Yeah. In LEP, it will not be produced. Higgs will not be produced, right?
No, it can be produced because center of mass energy is lost because we use ZA.
Okay, right. Yeah, okay, you are right. Yes. That should be checked.
Luminosity? What about luminosity?
No, that's a problem, but even on the casting, we don't know, like what kind of branching or
Yeah.
we don't know.
You have to check.
FCCE kind of situation you can probably think of.
In FCCEV, it will be probably a good channel to search. Yes. Okay. We also looked for other distributions. This is the transverse mass of the dilepton and missing ET system, which should be restricted by the Higgs mass because of the transverse mass kinematics. And this is the missing ET. So what we do is this. We now know that the Higgs to ZZ star to 2 neutrino 2 fermions are not is a reducible background, but there can be other backgrounds which can be very big in size. So we take all the other backgrounds and do a multivariate analysis using some more other variables, like we have 8 variables. And then here is some plot for the BDD classifier. Putting cut on different values of the classifier, I can calculate the sensitivity, and I use a cut on 0.99 or something for this analysis. So another thing, as we talked, that there can be invisible Z width, which will be effective for the derivative operators, and there is perturbative unitarity as well. So whenever we do EFT, we should actually do the perturbative unitarity, and we'll see it's actually important because.
What are those plots? I see signal you.
Oh, so signal is for one operator we chose DH chi chi. This is the signal.
Other things are background.
Others are different backgrounds, and we are seeing.
Decide.
Yeah. Yes.
How do you decide to classify the threshold?
Yeah. So as you see, if I put cuts on different values of the classifier, the backgrounds are reducing, and signal is almost a constant. If you put a cut on one,
This is in log scale.
this is in log scale. Yes. And actually I plot the sensitivity here, so we get an idea where we should put the cut on the classifier.
Did you show your variables that you get?
I have in my backup. I can show you. Yeah, I'll show you. So this is the thing for the derivative operators. This orange thing is the region that can be probed by semi-visible Higgs from the HL-LHC. The blue is what is already excluded by Higgs, Z invisible width, and these are the unitarity line. So generally we take unitarity at square root of S1 TeV. So in that case, the semi-visible Higgs is only sensitive to some mass below, say, 300. But in this case, Higgs decay, the scale of the system is around, let's say, actually we did ZH to calculate the unitarity bound, so it is 0.3 TeV. So it is sitting here. So we can probe a lot of region which is allowed by theory, reliable by the EFT interpretation. So generally the Z invisible width bound is much stronger, except for a few region where this sensitivity loses. For the Yukawa type operator, there is no Z invisible decay width bound, so semi-visible Higgs the only player in this case. For the Higgs to hadronic decay with the operators U phi with quarks, this is actually not very good. The sensitivity is not very good because the jet resolutions and other stuff kills it. Also, there is a issue with the cross section. Actually, I forgot. Somehow the cross section was smaller in this case.
But if you have say quad Higgs star matter casting, then you can also have Higgs plus say missing ET, mono Higgs plus missing ET.
From quark to Higgs, yes, we can have.
So that is also people start, right?
Mono Higgs plus met, yes.
Maybe you can also have this.
I think yes. Actually, we talked about this. Let's recall what happened to the mono Higgs. Yeah, I cannot recall. I can. Yeah. Yeah. So the last thing that we did is let's say we discover some excess in some EFT, then can we predict the UV from that excess? So in that case, we have to distinguish between operator structures. Okay, so given some kinematic distribution, which operator structure does it prefer? So in that case, we actually do the similar multivariate analysis with two structures. One is derivative operator, one is the Yukawa type operator that we had. And we have shown that you can actually distinguish those two operators very well. So this is not important for now, but in case of some like excess you see, this observation might be important. Or you can do this type of analysis with different EFT operator structures. Okay, the final thing is, if we remember, we were concerned about the Higgs neutrino floor, but here we see that if I do a similar plot like this that we had that they had in their paper, where so the LHC cannot go till the Higgs neutrino floor. With this analysis, we can actually wipe out the Higgs neutrino floor, which is sitting here, for the operators with leptons. For the operators with quark, actually my analysis is not that sensitive. You can make improvements on that analysis. So that still cannot reach the Higgs neutrino floor, but it does not mean it is not reducible. It is reducible, just the analysis is not that sensitive. So that's it. So I would say, like to summarize, we do semi-visible Higgs study where Z width is dominant for derivative operator, semi-visible Higgs is dominating for Yukawa type operators, and Higgs neutrino floor is reducible. Okay. What we didn't discuss here is this phi or chi can be dark matter, but we didn't explore the dark matter experiments or relic density and where this should stand in these plots. That we didn't explore. We just focused on the what we can see at the LHC with this particular channel. So yeah, with that I'll stop. Please ask if you have any questions. Yes. So yeah. So there is one point I would mention here is when I did which I didn't tell, is when I did the MVA, I actually did it in 3 parts. So for dark matter mass 1 to 20 GeV, I have 1 MVA. From 20 to 40, I have 1. Actually, I didn't plot it here, but 40 to 50, I have 1. So in each region, I cannot say that my dark matter mass is fixed. So, but you can train MVA with different, like 3 types of Monte Carlo input maybe. So in that case, I get a kind of similar sensitivity from all these 3 regions. So my analysis is not biased to any mass. So it is differently like sensitive to different masses, and those are kind of similar. So you get a like almost same kind of bound, not bound, but this can be explored at the HL-LHC. So I'd say this semi-visible Higgs may not be a great channel if you consider the dark matter bounds, because the direct detection thing will be much stronger than this. But you can have, let's say, for the leptonic case, the direct detection bound may be weaker. Indirect detection bounds can come, but then you can also do, let's say, co-annihilating dark matter or something like that to wipe out that. So in some small region, this may be useful, but the thing is that we should explore it in detail in the experiment that we neglected earlier.
Thank you.
Thank you.